In this video, we're going to talk about outliers, what they are, why they matter, and how we identify them in a principled way. In any real data sets, not all observations behave nicely. Some values sit far away from the bulk of the data, much larger or much smaller than what we would consider typical. These unusual values are called outliers, and outliers are important because they can strongly influence our summaries, our visualizations, and even our final conclusions. A single extreme value can shift the mean, inflate the standard deviation, stretch a graph, or change the story we tell about the data. So identifying outliers is not optional. It's a critical step in responsible data analysis. Outliers arise for many different reasons, and understanding those reasons is essential. Sometimes outliers are simply errors. For example, someone might accidentally type 500 instead of 50. Or a measuring instrument may malfunction and record an impossible value. In these cases, the outlier does not reflect reality. It reflects a mistake. But not all outliers are mistakes. Some represent rare but legitimate variation. Extremely high incomes, unusually long hospital stays, or exceptionally fast athletes may genuinely be different from the majority, and those differences may matter. In fact, sometimes the outliers are the most interesting part of the data set. They may signal unusual events, special populations, or meaningful departures from expected behavior. So we should never automatically delete outliers. Instead, we detect them systematically, investigate their source, and decide, based on context, how to handle them. Now, what actually counts as an outlier? There is no single absolute definition. What counts as far away depends on the scale of the data, the shape of the distribution, and the purpose of the analysis. Because of this, statisticians rely on rules of thumb, objective criteria that flag potential outliers. These rules don't automatically remove observations. Instead, they highlight values that deserve closer examination. Two of the most common approaches are the IQR rule and the Z-score rule. The IQR rule is based on the middle 50% of the data and is resistant to skewness and extreme values. The Z-score rule measures how many standard deviations a point lies from the mean and works best for roughly symmetric distributions. In this lesson, we're going to focus on the IQR rule. The IQR rule begins with the interquartile range. Recall that the interquartile range is defined as IQR equals Q3 minus Q1. Here, Q1 is the first quartile, the value below which 25% of observations fall. Q3 is the third quartile, the value below which 75% of observations fall. So the IQR measures the spread of the middle 50% of the data. It intentionally ignores the extreme tails of the distribution. That's important because it makes the IQR resistant to outliers. Once we compute the IQR, we define two cutoff values called fences. The lower fence is Q1 minus 1.5 times the IQR. The upper fence is Q3 plus 1.5 times the IQR. Any observation below the lower fence or above the upper fence is flagged as a potential outlier. The factor of 1.5 is a convention. It's not a law of nature. It represents a balance. If we made the multiplier too small, we would flag too many ordinary values. If we made it too large, we might miss truly unusual observations. Again, flag values are not automatically errors. They are simply values that deserve closer inspection. One major advantage of the IQR rule is that it is resistant. Because Q1 and Q3 depend only on the ranks of the data, not their magnitudes, extreme values have very little influence on the fences themselves. This makes the IQR rule especially effective for skewed distributions or heavy-tailed data sets. In contrast, rules based on the mean and standard deviation can be distorted by extreme values, because both the mean and the standard deviation are sensitive to outliers. So when data are skewed, the IQR rule is often the better choice. Let's look at an example involving fuel efficiency data. From earlier analysis, we computed the following quartiles for miles per gallon. Q1 equals 15.275, Q3 equals 22.8, and the IQR equals 7.525. Now we compute the fences. The lower fence equals 15.275 minus 1.5 times 7.525, which equals 3.9875. The upper fence equals 22.8 plus 1.5 times 7.525, which equals 26.5625. So any car with fuel efficiency below about 3.99 miles per gallon or above about 26.56 miles per gallon would be flagged as a potential outlier. When we examine the actual data, we find that no vehicles fall below the lower fence. However, 5 vehicles exceed the upper fence. Are these errors? No. These 5 vehicles are very light, highly fuel-efficient cars. They are unusual relative to the bulk of the cars in the data set, but they are not mistakes. They represent genuine differences in vehicle design. This example shows why we call them potential outliers. The rule flags them for investigation, but context tells us how to interpret them. Let's summarize. Outliers are observations that lie far from the bulk of the data. They can arise from errors, rare variation, or meaningful differences. We should never automatically delete them. Instead, we detect them systematically, investigate their source, and decide, based on context, how to handle them. The IQR rule provides a resistant, objective way to flag unusual values. It uses the middle 50% of the data to define fences and highlights observations that fall outside those boundaries. But identifying outliers is not just about applying formulas, it's about understanding the data generating process and thinking critically about what those unusual observations mean. And that combination, systematic rules plus thoughtful judgment, is what makes statistical analysis responsible and powerful.